Welcome to your very first video for the year, and I gave you a note sheet prior to class, so I'd like you to pause right now and go ahead and cut out the perimeter of this note sheet so that we can use that. Okay, so I have left the first two boxes together, and I'm not going to tape it down yet because I'm going to write around the edges and then I'll tape it, and I don't have to worry about writing over the tape. So the first two lessons were combining the first two sections of the book, and I'd like to review very quickly different number systems. So when you started counting with your natural numbers, and then you added nothing or zero, so that gave you whole numbers. Then you started to get to positive and negative numbers. We call those integers. And then you started to have rational numbers. We had fractions. Now all of these numbers are in what we call the real numbers. And they also include irrational numbers. Irrational. Things like 22/7, pi, things like that that are irrational. Those are real numbers. Now, within a broader scope, you have what we would include are imaginary numbers. And yes, we're going to use imaginary numbers this year. And remember, they come in the form a plus bi. But when you include imaginary numbers, you're broader than just real numbers. You are dealing with the complex numbers. And the reason I needed to review this is because sometimes we're going to ask you to only deal with one particular part of the numbers or one number set, and so you need to be able to identify them. SAT, PSAT, ACT also do this. All right, let's look at some examples. If you want to denote this set of 2, 3, 4, 5 in what we call set builder notation, then you're going to use this form. You're going to say that is the set of all x such that x is between 2 and 5, and x is the set of natural numbers, right? Now, let me ask you something. I said natural numbers because it only has 2, 3, 4, 5. It doesn't have any decimals, doesn't have zero. But the numbers 2, 3, 4, 5 are also whole numbers. They are also integers. They are also rational numbers. They are also real numbers. So this right here, where I said natural numbers, you could have actually said any of those, and it would be correct. Now let's do the set builder notation here. For x is less than or equal to -4. So we say it's the set of all x such that x is less than or equal to -4. And here I am going to say x is in the set of all real numbers, because all that says is it is less than -4. It could include everything, all the decimals, all the fractions. So you have to say real numbers. This one, x is less than 3 or x is greater than or equal to 27. So you have to give me both. Set builder would be the set of all x such that x is less than 3 or x is greater than or equal to 27. And again, x is in the set of all real numbers. Now, another way to denote these is with interval notation, and I will confess we prefer interval notation. I show you this because you still will see that. Sometimes we do that. You will see that on some of the testing, but mainly we want interval notation. Now, just as its name indicates, it is an interval. So you are going to tell me the beginning of the interval and the end of the interval. Well, right here, 2, 3, 4, 5 is not an interval. I know I start at 2 and I go up to 5, but it's not everything in between 2 and 5. It's not that interval. So this cannot even be written in interval notation. This, however, example 2, where we have x less than or equal to negative 4, that's everything less than negative 4. Now it includes negative 4, so we're going to put a sharp bracket, and we're also going to say negative infinity, and we put a parenthesis there because it does not include infinity. That's why you put the parenthesis, but here it said less than or equal to, so it includes the negative 4. You read this left to right. So you need to have the numbers, the lower numbers, which would be negative infinity, up to negative 4, and that's why the negative infinity goes first. Now this example right here, you're going to have to split this up because this is x less than 3. Well, that's everything from negative infinity up to 3. And it doesn't include 3. It's just less than, so it's a parenthesis. Also, it includes the 27. So we have 27, and x is greater than or equal to 27, so it goes to infinity. And that's how I would denote that notation. Okay, I'm going to tape this down, and then we are going to talk about functions. All right, I'll move this up a little bit. Here we go. All right, a function is what we call a relation of numbers. It's a relation, is a particular function. We define it as a function when, let's get a different color here. How about a purple? When each value of x, or we can call it the input, or we call it the independent variable. Now, when any of those correspond to exactly one value, okay, corresponds to exactly one value, then you get, it corresponds to exactly one of the value of y, or it corresponds to exactly one output, or it corresponds to the dependent variable. Then we say this relation is a function. Now, just a couple notes I want to say here. That the x value cannot repeat. So if you're looking at a table, for example, of the values for a particular relation or a particular equation, if any of the x values repeat, it is not a function. Also, this must pass what we call the vertical line test. To be a function. Now by that I mean it's a vertical line test. It's a line that goes straight up and down. And if you can draw that line and everywhere through the function, so you're obviously looking at the graph, but if it touches the graph more than once, if there's more x's, all right, repeat, then it's not a function. So the vertical line test has to only cross the graph one spot at every point. Okay? Now what we're going to do is we're going to evaluate some functions. Evaluating functions. When you do this, you need to remember your good old order of operations. And, very important, you need to watch the domain, because sometimes it doesn't exist within a certain area. For example, let's look at, let's call this example 4, that's where we are. Example 4, if I have f of x that equals x squared minus 2x minus 8, and I want to evaluate it at 4. Okay, so I'm going to take the function at 4 when x is 4, and you evaluate this. Use 4 everywhere there's an x. So I've got 4 squared minus 2 times 4 minus 8. So I have 16 minus 8 minus 8. Well, that's going to give me 0. Now I did that manually. Please practice doing this on your own as much as you can. You can also check it. You could put that in the calculator and look at the table to see what the value was at 4. Okay? Let's look at example 5. Example 5 is, I'm going to use the same f of x, so let me recopy that. But this time, I want you to find f at negative 3d. And you go, why would I do that and have to put the d in with the x? But that's where I want you to evaluate it. I want to evaluate it negative 3d. So you come to the equation, and everywhere there's an x, you evaluate it at negative 3d. Now this is very important. It says x squared, but the x is negative 3d. So it's negative 3d squared minus 2 times negative 3d minus 8. And just so that you don't lose a negative sign, sometimes it's very helpful to write all that out. All right, this right here, negative 3 squared is 9d squared. Negative 2 times a negative 3 would give you a positive 6d minus 8. And that becomes our answer. That's okay. All right. Example 6. Let's talk about one with a different domain. All right, so I want to know what's the domain of this function. You know what? I think this is a good place to stop. I will pick up here in the second video. Thank you very much.